we need to talk about VSEPR. And VSEPR, which makes no sense as an acronym, stands for valence shell electron pair repulsion. And this is one of the worst acronyms ever, because even after you write it, it's hard to figure out what it's really describing. Okay, but what it's really describing is a principle that determines the geometry of atoms, okay, of molecules. So let's take a look at what that might mean. Okay, of molecules. That's horribly written, but you get the idea. So let's take some molecule that we might be familiar with. Let's suppose we had like water. Now here's water, and when we draw it out, we start with this Lewis structure, and we usually draw it in a straight line. So it looks like, oh, I guess maybe water is linear. It's this straight molecule that has H bonded to O bonded to H. But it turns out that these electrons repel each other, right? And these electrons repel each other, right? And likewise these and these, right? So there's repulsions all the way around. And the problem is that in 2D, you think, oh, okay, but it's still as far apart as it can be. They're all 90 degrees. But if you actually look at this, if you say, okay, well, maybe from the side, it looks like this, where you have O and the two dots are up here, right? And then there's the H over here, and you can't see the two dots behind it. Maybe it's something like this. Well, then there's all this space up here and all this space down here that you're not using, right? And if we simply bring the H's a little bit down and the electron pairs a little bit up, then all of a sudden we've got a lot more distance between these electron pairs. And so what we say is that the electron pairs on the central atom and this is important, on the central atom, because on the central atom, because the electron pairs farther away from the central atom never get very close to each other, repel and spread as far apart as possible. Right. This determines the shape of the molecule. Okay, so let's look at water again. If I have four pairs of electrons around the central atom, right? I can think of this as being four groups of electrons repelling each other. Okay, so I've got two bonding pairs, right? I've got electrons in four different directions. Right? I've got two unshared pairs and two bonding pairs. Well, how do we spread four things around a central atom? Well, that's a little bit of a challenge. What we end up doing is we end up making a shape that looks a little bit like this, called a tetrahedron. All right, and you remember this maybe from geometry class, and probably you started calling it like a pyramid shape with a triangle base, but in reality this is called a tetrahedron. Let's bring this guy up here. And in a tetrahedron, we can describe the points. Two of them would be taken up by H's, right? Right? Our oxygen would be in the very center of our tetrahedron, right? And then we'd have unshared pairs at each of the other points, right? And so we'd have bonds that look like this, right? And so we'd have this sort of bent molecule where we thought we had a linear molecule. And you're like, wait, bent seems closer together than linear. But don't forget, it puts the electron pairs much farther apart, right? So now it turns out that this angle between the electron pairs is about 105 degrees, right? And the angle between this pair and the electron pair is also about 105 degrees. So what we've done is we've changed, by using a tetrahedron, or a tetrahedral arrangement, if we want to use an adjective, the angles go from 90 degrees to 105. And that's a lot bigger angle and a lot smaller repulsion, okay? So if you look at this, we've increased the angle about 15 degrees by spreading it out over 3 dimensions, okay? Now, this tetrahedron thing is, essentially is 4 things, right? 4 groups of electrons symmetrically arranged around the center point. Okay. Now we can have other arrangements as well, and we classify them based on how they're distributed around that center point. And so let's take a look at some of these possible shapes. So if I had something, for example, H2CO, right? Something like this. We could draw the structure. In fact, let's actually go through the whole process. We have H2CO. So we have 2 plus 4 plus 6 electrons, right? Which is 12 electrons. And we can draw our Lewis structure, right? H, C, H. C is in the middle because it needs the most bonds. And we draw our skeleton like this, and we find that it has 2, 4, 6, 8, 10, 12, 14 electrons. But we only have 12, so we need an extra bond. And so we'll put that extra bond in, and we'll get this structure. Okay, so here's our Lewis structure. And so we always start analyzing the geometry by having a Lewis structure. Now, if I look at this Lewis structure, it has, the carbon has 3 bonded atoms. Now I stopped looking at the bonds because it turns out that this is one group of electrons, right? That double bond can't separate from itself, and so it counts as one group of electrons, right? This is also one group of electrons, this pair, right? And so is this, one group, okay? So we don't distinguish between double and single bonds because they're just clusters of electrons that repel each other. So instead of counting the bonds, because it looks scary, it looks weird to say, well, that's the same as that, let's just count the bonded atoms, and then we ignore whether it's a double or single bond altogether. It has 3 bonded atoms, and it has no unshared electrons. And so what we're going to do is we're going to call this an A for the central atom, X3 for the bonded atoms, E0, right, for the unshared pairs. And the reason we give it this name is because we're going to figure out the geometry of this, and then anytime we see something else that fits this description, we'll quickly identify its shape, because we can say, oh, okay, that's just another one of those AX3 zeros, and so I already know its shape. So what is this? Well, that's 3 things arranged around a central atom. And 3 things around a central atom are clearly going to be at the points of an equilateral triangle, right? So 3 things. Is just going to be triangular planar, we call it, right? And so we'll have 2 H's here and here, right? Our central atom C will be in the middle, and then our oxygen O will be at the top, right? And then we can draw our double bond, single bond, and so forth. And so we get this triangular planar arrangement, okay? So we can tell what shape it is very quickly. And so there are 3 things symmetrically arranged. So it's going to be this triangular arrangement. And so we can make effectively a chart of these shapes that we would find. And there's patterns in this. For example, if I have 2 things symmetrically arranged, then I just have something like this. Right? If I have 2 atoms bonded to a central atom and no unshared pairs, I would call this an AX2E0. And we'd say that this is simply a linear arrangement, because 2 things symmetrically arranged are the farthest apart they can be is at 180 degrees. Okay, so linear. If I have 3 things symmetrically arranged, I have my triangular planar arrangement. So X. So this would be our AX3E0, and that's triangular planar. Right, flat triangle. Right. If I have 4 things arranged around the central atom, and I'll try to sort of draw this in perspective. In other words, that we have this arranged, this is a little hard to see, around the sides of a tetrahedron, like this, right? Then we have our AX4E0, and that's a tetrahedral arrangement. Right, tetrahedral arrangement. Okay, so we've got all of these shapes. Whoops, let's actually get the writing in there. But the thing is, 4 groups of electrons don't have to be 4 bonded pairs, right? 3 groups of electrons don't have to be 3 bonded pairs. I can actually have unshared pairs in there as well. For example, in the water, I had 2 unshared pairs. So for example, in the triangular arrangement, I can have an A and 2 atoms, X and X, and then I can have an unshared pair up here. Okay. In this case, I still have my triangle. You can see I still have that triangle arrangement, but I only see the atoms, right? We don't really, the lone pairs, they repel, but they're very, very small, and we don't think of them as taking up space, even though they're repelling. And so we call this an AX2E0, or E1, right? AX2E1. And this one we're going to call bent. And if you're being precise, we're going to call it bent 120 because there's another bent. And so we'll say bent 120 because this angle is still 120 degrees. This angle is also 120 degrees, right? If I have three angles that add up to 360, each angle is 120. And so I get the same angle because really I have the same number of electron pairs. And so what I'll say that I can specify what's called the electron geometry, right? In addition to the molecular geometry. Oops, let's bring this down. Right? And the molecular geometries are all these shapes, but the electron geometry here would just be linear. I don't really have any choice for two objects. I just have a linear arrangement. This one I'm going to call triangular planar. Because both of these have three groups of electrons arranged in a triangular planar arrangement. But I give this one its own name for a shape because I can't see that third corner. And this one will be based on our tetrahedron, so tetrahedral. So I'll have this electron geometry based on the total number of groups that are doing the repelling. So this one I'm going to call bent 120. Well, I have two more for this because here I can only substitute one pair of electrons before I get down to two atoms. So for the tetrahedral arrangement, I can simply lop off a vertex, and I'll keep my central atom A, and I'll keep my side atoms here, A and A, right? Oh, sorry, X and X. Right? So I've got these things arranged in sort of a tripod-looking thing, but then I have an unshared pair at the top. I still have that sort of tetrahedral arrangement, if you look, right, for my shape, but I can't see the top vertex. And this is my AX3E1, right? And I'm going to call this a triangular pyramid. Right? And truthfully, triangular pyramid is kind of a crummy name for it. I like to think of it as sort of a tripod shape. Unfortunately, the rest of the world doesn't agree with that name, but if you remember that, you can see why that shape would be the way it is. Right? So we've got these three electrons pushed, these three bonded atoms pushed downward by this unshared pair, and so we end up with this triangular pyramid arrangement. I can also pull two of the atoms off of here, like I did with water, and I can have just two left, and I'll still have my central atom. Okay, and here are my bonded atoms, and now I've cut off both corners that are left. And I still have my sort of tetrahedral electron arrangement, but overall, right, I'm going to call this one bent. Oh, sorry, I should actually call it an AX2E2, and I'll say that it is bent. But it's not bent 120. This angle is smaller. This angle is about bent 105. Right? Because the angles within a tetrahedron are about 109.5. And you might say, well, why is this smaller? Why is this 105? And the answer is that unshared pairs of electrons, while I've drawn them at exactly the same location as the bonds, actually sit closer to the central atom because they're not shared by anybody. And so these guys would actually sit closer to the central atom, and they have a little bit more repulsion than bonding pairs. And so this would be bent 105. And so now we have 6 possible shapes for a substance that follows the octet rule. There are also shapes for ones that don't follow the octet rule, but we're not going to focus on that most of the time. Instead, you can look those up on a chart when you come to them. Okay, so here are our shapes. So let's walk through how we could figure out the shape of something. And let's take just some structure like, I don't know, CH2Cl2, right? So if we have this structure, CH2Cl2, then we'd have, let's see, 4 plus 2 plus 14, right? So 20 electrons. Put our carbon in the middle, H's around it, our Cl's around it, because Cl and H all only take one bond without causing formal charge. We draw in our octets, leaving duets for hydrogen. And now we have this structure, which has 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 electrons. So since it matches, we're done, and this is our structure. We can then say, well, this is an AX4, right? And since it's an AX4, it must be a tetrahedral shape. And so if I were, making this, I would have my carbon in the middle, and I'd have H's on 2 of the corners of a tetrahedron, and I'd have Cl's, right, on the other corners. So I'd have something like this. And this doesn't look very convincing to you because I've drawn it in 2 dimensions, right? But I'm trying to represent something in 3 dimensions. So what do? Well, what we can do is we can use a modeling program. In this case, I'm going to go to PhET and use a modeling program that they have. And if I click on something like this, right, it allows me to create a 3-dimensional structure. So in the case of our CH2Cl2, I can simply tack 4 things around our central atom. And you can see that we have something that looks tetrahedral. And if I spin it around, you can see it looks a lot like the shape that I drew. Okay, so, whoa, there it goes, right? And so if that were my carbon, and those 2 were H's, or sorry, this one and this one were H's, and these 2 were Cl's, we'd have the picture I drew on the page before. But I can also remove a couple of these bonds and put unshared pairs there. And then if you were to go back, you would see that we have something that looks, whoa, let's spin it around, something not unlike, whoops, let's put this guy up top, and then spin this slightly that way, and I have the water molecule I drew before, right, where I have this bent water molecule. Okay, oops, let's bring it back. Maybe a little tough for me to navigate this thing, but there it is. Oh, there's my water molecule. Okay. And I could also have my CH2O if I take away one of these unshared pairs, and I simply put a double bond on there. And now I have something that is completely flat. You can see it's flat. But if I spin it around, you can see that I have a triangular shape, triangular planar, right? So here's my triangle. But if I spin it so that they're all together in the plane, you can see that it's flat, right? And there's my flat triangle. Okay, so those are the structures I drew, and a modeling program allows us to see these things in 3D. Further, if I wanted to, I could type in molecular model. Let's try CH2O and see what we get. And images, right? And we get different pictures of molecules connected in the same manner. And you can see that we get this, right? Which is another 3-dimensional picture. And they actually sell modeling kits to allow you to play with these like Tinker Toys. So you can slap these together and see what the actual look like in 3D. So VSEPR is simply a way of going from a Lewis structure like this to a shape, right, like this one over here, okay? And it allows us to tell what the actual geometries of the things we've been describing in class are. Excellent. Let's stop there.